Everyone is talking about the interstellar comet 3I Atlas. But that's not the object that should make you rethink our place in the solar system. Somewhere out in the dark, something impossibly large is falling toward us from the outer reaches of space, and almost no one knows it's there. It's not fast, not flashy, not making headlines with dramatic close approaches or interstellar mysteries. It's just there, sliding slowly inward through the black, enormous beyond comprehension, moving on a path that shouldn't exist according to everything we thought we knew about our solar system. This is C2014 UN271 Bernardinelli Bernstein, and by the time you understand what it really is, you'll see why this quiet giant changes everything we thought we understood about the cosmic neighbourhood we call home. Let me put this in perspective for you. While everyone has been captivating themselves with the story of interstellar visitors like 3I Atlas, those small fleeting objects that zip through our system once and vanish forever, this thing has been slowly, patiently approaching from a distance so vast that light itself takes hours to cross it. Its nucleus, the solid core of ice and rock at its heart, stretches somewhere around the width of a small moon. Not a boulder, not a mountain, but a world unto itself, wrapped in ancient ice that has seen nothing but darkness and cold for hundreds of thousands of years. When I say it's the largest Oort Cloud comet ever measured, I'm not exaggerating for effect. This object sits in a category that makes astronomers uncomfortable, because it blurs every line we've drawn between comet and dwarf planet, between visitor and resident, between what should be out there and what we thought could never come this close. Its orbit is a slow, patient curve that takes it from the absolute edge of the sun's gravitational influence, a realm so distant and empty that it might as well be interstellar space, all the way in to a point just beyond Saturn's orbit, where it will make its closest approach in early 2031. That journey from aphelion to perihelion and back out again takes on the order of 1 million years. Read that again. Roughly 1 million years for a single orbit. When this object last passed through the inner solar system, our species didn't exist. No cities, no agriculture, no written language. Just scattered bands of early hominids figuring out fire and stone tools, staring up at a sky that held this same silent giant somewhere in its depths, unnoticed and unnamed. And here's what should make you pause. This thing is bound to our sun. It's not an interstellar visitor passing through once and never returning. It's ours. It belongs to the same gravitational family as Earth, Mars, Jupiter, and everything else orbiting our star. But its orbit is so extreme, so wildly eccentric and tilted, that it spends almost all of its existence in a frozen graveyard far beyond the realm of planets, where the sun is just another bright point in the black. Most comets we know follow predictable, relatively shallow paths. They come in, swing around the sun, maybe put on a show for a few weeks or months, then head back out. Bernardinelli Bernstein doesn't do that. It moves like something that was violently redirected, thrown onto a path that slices through the plane of the planets at a very steep angle, far from the gentle, orderly disk where most worlds orbit. It's moving like it was shoved. So let's be very clear about what makes this stranger than the objects that have dominated the conversation. When people talk about 3I Atlas, or other interstellar comets, they're talking about small fragments, a few kilometers across at most, following hyperbolic trajectories that carry them past the sun once and then out into the galaxy forever. Those objects are fast, exotic, and gone. Bernardinelli Bernstein is the opposite. It's massive, slow, returning, and gravitationally shackled to our star, but behaving as if it came from somewhere so far and so strange that the rules we use to predict normal comet behavior barely apply. The sheer scale gap between a typical interstellar visitor and this thing is like comparing a pebble to a house. Actually, it's worse. It's tens of thousands of times more massive, and unlike those fleeting visitors, this giant is already showing signs of waking up, venting gas from its surface at distances where most comets would still be frozen solid and inert. That brings us to the questions that should be echoing in your mind right now, because they're the same ones astronomers are quietly asking each other when the cameras are off and the press releases are written. Why did this giant choose now to come in from the deep freeze? What nudged it out of its distant orbit after millions of years of stillness? And perhaps most unsettling of all, what else might be sliding in behind it? Too far and too dark for us to see yet, but already on its way. Stay with me, because over the next stretch of time we're going to trace this object's path from the edge of the Oort Cloud to its slow rendezvous in 2031. We're going to explore why its orbit is so disturbingly wrong, why it's already active at distances that defy simple models, and what that tells us about the true shape and hidden population of our solar system. We're going to look at the forces that could have nudged something this massive onto such a twisted path, and we're going to ask whether Bernardinelli Bernstein is an anomaly, or the first clear look at a whole class of silent giants we've been blind to until now. By the end, you'll understand why this object isn't just a curiosity or a data point. It's a window into the deep structure of the space around us. A reminder that the solar system we think we know is only the bright, warm, well-lit part of a much larger, darker and stranger place. And if objects like this make you rethink how safe and simple our cosmic neighbourhood really is, do me a favour. Hit the like button so we can keep following this giant slow fall together, and drop a comment telling me where you're watching from in the world. Because when we talk about visitors from the dark, things that spend lifetimes in the cold and only briefly pass through the light, it helps to know who else is out there with us, paying attention, thinking the same questions, feeling that same quiet pull of curiosity and unease. Now, let's begin at the beginning, out where the darkness is total and the cold is absolute, and watch this giant emerge. Out beyond Neptune, beyond Pluto, beyond the scattered disk where the last known dwarf planets wander in their lonely elliptical paths, there is a region of space so vast and so empty that it almost defies imagination. This is the Oort Cloud, a spherical shell of icy debris that surrounds our solar system like a distant frozen halo, stretching outward for tens of thousands of astronomical units, distances so large that even travelling at the speed of light, you'd be crossing empty blackness for weeks or months. It's a graveyard of primordial material, leftovers from the formation of the planets, objects that were flung outward by gravitational encounters with the giant worlds, and now orbit in slow, patient silence, so far from the sun that its light and heat are virtually meaningless. Most of these objects are small, invisible, and will never be seen by human eyes, but some of them are not small, and one of those rare giants is now making its way toward us. C2014 UN271 Bernardinelli Bernstein is not a typical comet. When astronomers first began analysing the data and calculating the size of its nucleus, the solid, icy core at the centre of the growing cloud of gas and dust, they had to double-check their numbers. The initial estimates suggested a nucleus somewhere in the range of over 100 kilometres across, possibly as large as 140. That's not a rock. That's not even a mountain range. That's a world. A dark, frozen, ancient world wrapped in layers of ice that have barely changed since the solar system was young. To put that in perspective, most comets that swing past the sun and light up our skies with beautiful tails have nuclei only a few kilometres wide, maybe 10 or 20 at the very most. Bernardinelli Bernstein is an order of magnitude larger than that. It's the largest comet nucleus ever measured, and by a significant margin. In fact, it sits in a category that makes scientists uncomfortable, because at that size, the line between comet and dwarf planet starts to blur. This is an object massive enough that its own gravity has likely pulled it into a roughly spherical shape, something that only happens when you have enough material and enough mass for self-gravity to dominate. And yet, despite that size, it is still fundamentally a comet. It is made primarily of ice, water ice, frozen carbon monoxide, carbon, dioxide, methane, ammonia, and other volatiles that froze out of the primordial nebula when our solar system was forming. It is not rocky like the asteroids of the inner system. It is not a captured wanderer from another star. It is ours, born here, thrown outward billions of years ago when the giant planets were still settling into their final orbits and flinging debris in all directions. This thing is a time capsule, a pristine sample of the material that once swirled in the outer reaches of the protoplanetary disk, now preserved in a deep freeze for most of its existence. And now, after hundreds of thousands of years in the outer darkness, it's coming back. Right now, as I'm speaking to you, Bernardinelli Bernstein is somewhere in the outer solar system, still far from the sun but moving steadily inward, already closer than it has been in living memory, or in any memory at all, given that its last pass through this region predates human civilization by hundreds of millennia. Current observations place it at a distance measured in tens of astronomical units, well beyond the orbits of the outer planets, but no longer in that utterly remote realm where the Oort Cloud truly begins. It is descending slowly but inevitably, pulled by the Sun's gravity along a path that will bring it to its closest approach in January of 2031. At that point, perihelion, the nearest point in its orbit to the Sun, will place it just beyond Saturn's orbit, a little over 10 astronomical units from the Sun. That's still far enough that the Sun, even at closest approach, will appear only as a very bright star, not the blazing disk we see from Earth. The warmth it receives will be minimal, the sunlight dim. And yet, even at that distance, this giant is waking up. Think about that for a moment. Most comets don't start showing significant activity, venting gas, forming a coma, developing a tail, until they get much closer to the Sun, usually inside the orbit of Jupiter, where temperatures rise enough for water ice to begin sublimating directly from solid to gas. But Bernardinelli Bernstein started showing signs of a coma and outgassing activity much earlier, at distances where the sunlight is so weak that water ice remains frozen solid. Observations from facilities like the Atacama Large Millimeter Array, one of the most sensitive radio telescope systems on Earth, detected carbon monoxide gas streaming from the comet's nucleus when it was still far beyond the traditional ice line. That's unusual. That tells us that the surface of this object is not just ordinary water ice. It's rich in more volatile ices, substances that can vaporize at much lower temperatures, things like carbon monoxide and carbon dioxide. These are the same materials that were abundant in the cold outer regions of the early solar system, and finding them now, streaming off the surface of a giant comet, is like watching a sealed time capsule begin to vent ancient air before anyone has even opened it. The orbital period of this object is staggering. Current best estimates place it somewhere around 770,000 years, possibly longer, depending on subtle gravitational perturbations we can't fully account for yet. That means this comet last reached perihelion when the Earth was in the grip of an ice age, when the ancestors of modern humans were scattered across Africa and Eurasia in small, nomadic groups, when the night sky looked almost exactly as it does now, except for one faint, slow-moving point of light that no one would have noticed or named. And when it completes this pass and begins its long fall back out into the dark, it will not return until the year roughly 770,000 from now, a span of time so incomprehensibly long that whatever intelligent life exists at that point, if any, will have no memory of us, no records of this moment, no way to know that we were here, watching this giant as it moved through. So why is it coming in now? What set this enormous, ancient block of ice on a path that brings it from the edge of interstellar space back into the realm of the planets? That's the question at the heart of everything else. Comets don't just decide to fall inward on their own. Something has to nudge them. Something has to change their orbit, tweak their trajectory, give them just enough of a gravitational kick to start the slow, inevitable descent toward the Sun. For most long-period comets, the answer is straightforward. Passing stars, the slow pull of the galactic tide, random perturbations from the combined gravity of distant objects. The Oort Cloud is not a stable, static place. It's a dynamical reservoir, constantly being jostled and stirred by forces both internal and external to the solar system. Over millions of years, some objects get nudged inward, some get flung outward into interstellar space, and a lucky few fall onto paths that bring them close enough to the Sun for us to see them and study them. Bernardinelli Bernstein is one of those lucky few. But its orbit is not typical, its size is not typical, and the timing, the angle, the sheer improbability of something this large showing up now raises questions that go deeper than simple galactic dynamics. Some researchers, in early analyses and preprints, have started to suggest that the existence of an object this large, on an orbit this extreme, might imply that our models of the Oort Cloud's population are incomplete. Maybe there are more of these giants out there than we thought. Maybe the formation and ejection processes that populated the Oort Cloud in the first place were more efficient at preserving large bodies than our simulations assumed. Or maybe, and this is where the conversation gets more speculative, more uncertain, there are forces at work in the outer solar system that we don't fully understand yet, subtle gravitational influences from unseen masses, or long-term resonances with structures we can only guess. At Planet 9, the hypothetical distant world that some astronomers believe might be lurking far beyond Neptune, has been invoked as one possible explanation for why some objects in the outer system have strange clustered orbits. Could something like that also play a role in nudging Oort Cloud comets inward? It's possible, it's debated, it's not proven. But the fact that we're even asking the question tells you how unsettling this object is. And here's the thing that keeps pulling at me, the thing I want you to feel as we move forward. We're watching something that spends almost all of its existence in total darkness, in cold so profound that molecular motion nearly stops, in a region of space so far from anything that the concept of neighbour has no meaning. And yet, for this brief sliver of time, a few decades out of hundreds of thousands of years, it is visible to us. It is here, close enough to study, close enough to measure, close enough to watch as it wakes up and begins to remember what it means to be near a star. That is not just a scientific opportunity. That is a cosmic event, a moment of intersection between human curiosity and the deep, slow rhythms of the solar system's outer machinery. We are living in the narrow window when this giant is passing through our light, and when it leaves, it will not return within the lifetime of any civilization we can imagine. So what happens next? How do we make sense of something that defies the neat categories we've built? How do we understand an orbit that seems designed to confuse, a size that shouldn't exist, and a path that raises more questions than it answers? That's where we go now, into the geometry of the impossible, into the shape of an orbit that breaks every pattern we thought we knew. If you've ever looked at diagrams of the solar system, you know the picture. A neat, orderly disk of planets, all orbiting the Sun in roughly the same plane, all moving in the same direction, like runners on a circular track. Mercury, Venus, Earth, Mars, the asteroid belt, then the giants, Jupiter, Saturn, Uranus, Neptune. Everything arranged in concentric circles, tilted at most by a few degrees from the ecliptic, the imaginary plane defined by Earth's orbit. It's tidy, it's predictable, it's the structure that lets us build models, make predictions, send spacecraft across billions of kilometers with confidence that they'll arrive exactly where and when we planned. This is the solar system we know, the one we've mapped and measured, the one that feels, if not safe, at least comprehensible. And then there's Bernardinelli Bernstein, moving through that same space like a knife through silk, cutting across the plane at an angle so steep it might as well be perpendicular. Let me explain what I mean by that, because the geometry here is not just unusual, it's profoundly wrong in a way that demands explanation. The orbit of Bernardinelli Bernstein is what astronomers call highly eccentric, meaning it's not even close to circular. In fact, its orbital eccentricity is so extreme, hovering very near the upper limit of what a bound orbit can be, that the difference between its closest and farthest points from the Sun is almost unimaginable. At aphelion, the farthest point, this thing is out in the deep Oort Cloud, tens of thousands of astronomical units from the Sun, so far that the Sun's gravity is barely distinguishable from the pull of passing stars and the galactic tide. At perihelion, the closest point, it will be just beyond Saturn, a little over 10 astronomical units out. That range, from the edge of the solar system's gravitational influence all the way into the outer planets, is a journey of such colossal scale that it takes hundreds of thousands of years to complete. And the shape of that orbit, the elongated ellipse it traces, is almost indistinguishable from a straight line for most of its length, only curving sharply when it gets close to the Sun and whips around for the return journey. But eccentricity is only part of the story. The other part, the one that makes this orbit truly strange, is its inclination. Most objects in the solar system orbit within a few degrees of the ecliptic. Even long-period comets, which come from the Oort Cloud and can have highly eccentric orbits, usually have inclinations that are at least somewhat aligned with the planetary disk. Bernardinelli Bernstein does not. Its orbit is inclined at roughly 95 degrees to the ecliptic. Think about what that means. An inclination of 0 degrees would mean it's orbiting in the same plane as Earth. An inclination of 90 degrees would mean it's orbiting perpendicular to that plane, moving straight up and down relative to the disk of planets. Bernardinelli Bernstein is tilted just past 90, which means it's slightly retrograde. It's not just moving perpendicular to the planets, it's moving in the opposite direction, like a coin spinning on a table that's been flipped upside down and sent rolling through the middle of a carefully arranged set of concentric rings. This is not a natural undisturbed orbit. This is the orbit of something that was violently perturbed, redirected by forces strong enough to twist its path out of the plane entirely and send it falling inward from a region where no human-made instrument has ever reached. Now compare that to the interstellar visitors we've seen. Objects like 3I Atlas come into the solar system on hyperbolic trajectories, meaning they're not bound to the sun at all. They pass through once, pick up a gravitational assist or just coast past, and then head back out into interstellar space, never to return. Those trajectories are shallow, fast, and unbound. They're the paths of objects that have no loyalty to our star, no history with our system, no reason to stay. Bernardinelli Bernstein is the opposite. It's deeply bound. Its orbit, despite being wildly elongated and tilted, is still an ellipse. It will come in, it will swing around, and it will go back out, only to return again in the distant future. That binding, that gravitational shackle to the sun, is what makes it one of ours. But the shape and angle of that binding are so extreme, so far outside the norm, that they scream for an explanation. Something put it on this path. Something redirected it from whatever orbit it originally had and sent it on this long, slow, tilted fall through the solar system. What could do that? The most straightforward answer is a close encounter with another massive object, something with enough gravity to significantly alter the orbit of a body this large. In the early solar system, when the giant planets were still migrating and settling into their current positions, there were likely many such encounters. Small bodies, planetesimals, proto-comets, anything in the wrong place at the wrong time could be flung outward or inward by a near pass with Jupiter or Saturn, or one of the other giants. That process, known as planetary scattering, is how we think the Oort Cloud was populated in the first place. Objects that formed closer to the Sun, in the region where the giant planets now orbit, were gravitationally kicked outward, over and over, until they reached distances where the Sun's gravity was weak enough that they could settle into stable distant orbits. Bernardinelli Bernstein could be a survivor of that era, an object that was scattered outward billions of years ago and has been orbiting quietly ever since, its path slowly evolving under the influence of galactic tides and distant stellar passes. But here's where it gets tricky. When you try to back-integrate the orbit, when you run the mathematics in reverse and ask where this object was and what its trajectory looked like, tens of thousands or hundreds of thousands of years ago, the picture becomes less clear. Standard models can explain most of the features: eccentricity, long period, general inclination. But the precise combination of those features, especially the extreme tilt and the timing of its current inward fall, is harder to pin down to a single definitive cause. Maybe it was a stellar flyby, a star that passed close enough to the outer Oort Cloud 1 million years ago and gave this object just enough of a nudge to start it falling. There have been several such flybys in the past few million years, and astronomers have catalogues of nearby stars whose past trajectories brought them within range of our system's outer envelope. But matching a specific flyby to a specific comet is difficult, because the Oort Cloud is so vast and the perturbations are so subtle. Or maybe it's the galactic tide, the slow rhythmic pull of the Milky Way's gravitational field as we orbit the galactic centre. That tide isn't constant. It varies depending on where we are in our orbit, and it can slowly change the energy and inclination of Oort Cloud objects over millions of years. Combination of tide and random encounters could, over time, produce an orbit like Bernardinelli Bernstein's. But again, the exact sequence of events, the precise history, remains uncertain. And then there's the more speculative possibility, the one that some researchers mention quietly in conference hallways and preliminary papers, but haven't yet proven: the influence of an unseen distant planet. Planet 9, if it exists, would be a world several times the mass of Earth, orbiting far beyond Neptune, taking thousands of years to complete a single orbit. Its gravity would be weak at any given moment, but over millions of years, it could shepherd the orbits of distant objects, creating clustering patterns and unusual inclinations. Some of the evidence for Planet 9 comes from the orbits of trans-Neptunian objects, bodies in the scattered disk and beyond that seem to have their perihelia aligned in ways that are hard to explain by chance alone. Could something like that also affect Oort Cloud comets? Could a distant massive planet slowly tug at the orbits of objects like Bernardinelli Bernstein, nudging them onto paths that eventually bring them inward? It's possible, but it's not confirmed, And as of now, Planet 9 itself remains hypothetical. We have suggestive evidence, we have models, but we don't have a direct detection. So invoking it to explain Bernardinelli Bernstein is, at this stage, more of a hint than an answer. What we do know, with certainty, is that this orbit is not the result of calm, gradual evolution. This is not an object that has been quietly circling the Sun on the same path for billions of years. Something happened, something changed, something took a massive block of ice, possibly one of many such blocks scattered throughout the Oort Cloud, and redirected it onto a trajectory that now brings it through the planetary zone, tilted almost 90 degrees, moving slowly but inexorably toward the light. And when I say something, I don't mean anything mysterious or artificial. I mean some combination of gravitational forces, encounters, resonances, and perturbations that we are still working to fully understand. The solar system is not a static clockwork mechanism. It's a dynamic, evolving system, and the Oort Cloud, far from being a stable reservoir, is a constantly shifting population of objects whose orbits are shaped by forces both internal and external. Bernardinelli Bernstein is proof of that. It is an object whose orbit tells a story of violence and chance, of being in the wrong place at the wrong time, or perhaps, from our perspective, exactly the right place and time, because it means we get to see it, study it, and learn from it. So, as it continues its slow descent, cutting through the plane of the planets like a diver entering water, we have to ask ourselves, what else is out there, following similar paths, nudged by similar forces, but still too far or too faint for us to detect? How many other giants are sliding inward right now, decades or centuries away from their own perihelion passages, waiting to be discovered? And what does the existence of this one, this impossible, beautiful, terrifying outlier, tell us about the hidden architecture of the space we inhabit? That's the question we'll start to answer next, as we watch this giant do something even stranger. Wake up far too early and begin to breathe. There's a moment in the life of every comet when it stops being just a frozen rock drifting through space and becomes something alive, something dynamic. It happens when the comet gets close enough to the Sun that the ice on its surface begins to warm, to crack, to sublimate, turning directly from solid to gas without ever becoming liquid, and streams of vapour start escaping from the nucleus, carrying dust and debris with them. That's when a comet develops a coma, a glowing cloud of gas and dust that surrounds the nucleus and reflects sunlight, making the comet visible from Earth even when the nucleus itself is too small to see directly. It's when the tail forms, that iconic streamer of material blown back by the solar wind and radiation pressure, stretching for millions of kilometres behind the comet as it races through the inner solar system. It's the moment when a comet transforms from an invisible, inert object into one of the most beautiful and dramatic sights in the sky. And for most comets, that moment happens relatively close to the Sun, inside the orbit of Jupiter usually, and often much closer, within the orbit of Mars or even Earth, where the sunlight is strong and the temperature's high enough for water ice to actively boil away. Bernardinelli Bernstein is not playing by those rules. It started waking up much earlier, much farther out, in a region of space where the sun's warmth is barely a whisper, and the temperatures should be cold enough to keep everything frozen solid. And that tells us something profound about what this object is made of, what it has preserved, and how it has changed, or hasn't changed, over the billions of years since it first formed. The first signs of activity were subtle. As astronomers tracked Bernardinelli Bernstein's position and brightness over months and years, they noticed that it was slightly brighter than expected for a bare nucleus at that distance. There was a faint, diffuse glow around it, a coma that had no business being there yet. At first, there was some debate. Was it real activity, or just an artifact of imaging, a trick of the light? But as more observations came in, including high-resolution images from the Hubble Space Telescope and spectroscopic data from ground-based observatories, the answer became clear. This thing was outgassing. It was venting material from its surface, creating a cloud of gas and dust that surrounded the nucleus and reflected sunlight, making the comet appear larger and brighter than the solid core alone would account for. And when radio, telescopes, particularly the Atacama Large Millimeter Array, turned their attention to it, they detected something even more specific: carbon monoxide. Not water vapour, not the usual suspects that appear when comets get close to the Sun, But carbon monoxide, one of the most volatile ices that can form in space, something that can sublimate at temperatures far below the point where water ice would even begin to soften. This was happening at a distance of well beyond 15 astronomical units, farther from the Sun than the orbit of Uranus, in a part of the solar system where the sunlight is so dim that it's barely distinguishable from starlight, where the temperature hovers only a few dozen degrees above absolute zero. And yet, Bernardinelli Bernstein was already active, already shedding gas, already showing signs of the transformation that would accelerate as it continued to fall inward. In fact, the detection of carbon monoxide outgassing at such a distance made this the most remote comet ever observed, producing detectable millimeter wave emissions from volatile sublimation. That's a record, but more than that, it's a clue. It tells us that the surface of this object is not just ordinary water ice mixed with rock. It's rich in hypervolatile ices, substances like carbon monoxide, carbon dioxide, methane, and other molecules that froze out of the Primordial nebula when the solar system was young and have remained locked in the solid state ever since, preserved in the deep freeze of the Oort Cloud. Think about what that means. These are the same ices, the same molecules, that were abundant in the outer protoplanetary disk when the planets were forming. They're the building blocks that went into making the giant planets and their moons, the materials that rained down onto the surfaces of Europa and Enceladus and Titan, creating the subsurface oceans and organic-rich atmospheres we see today. They're the ingredients that may have seeded the early Earth with water and organic compounds, delivered by cometary impacts when our planet was still molten and cooling. And now, here, in the form of Bernardinelli Bernstein, we have a nearly pristine sample of those ancient ices, barely altered since they first condensed out of the swirling gas and dust around the young sun. By studying the composition of the gases streaming off this comet, by measuring the ratios of different isotopes and the abundances of trace molecules, scientists can reconstruct the chemical conditions of the early solar system with a level of detail that's impossible to get from planets or moons, which have been geologically active and chemically altered over billions of years. This is a time capsule in the most literal sense, a sealed container of primordial material that is only now, after hundreds of thousands of years in the outer dark, beginning to open and vent its ancient contents into the space around it. And it's not just carbon monoxide. As Bernardinelli Bernstein continues to approach the Sun, as the sunlight grows gradually stronger and the surface temperature rises by fractions of a degree, other ices will start to sublimate. Carbon dioxide, which freezes and sublimates at temperatures slightly higher than carbon monoxide, is likely already joining the outgassing mix, and water ice, the dominant component of most cometary nuclei, will begin to contribute as the comet gets closer to the inner solar system. By the time it reaches perihelion in 2031, Bernardinelli Bernstein should be fully active, with a bright coma and possibly even a visible tail, despite the fact that it will still be far beyond the orbits of the inner planets. Observers on Earth with good telescopes will be able to watch it, to track its changes, to measure the composition and density of the gases and dust it's producing. And because this object is so large, because it has so much material to shed, that activity could continue for months or even years, giving researchers an extended opportunity to study a truly pristine comet in ways that have rarely been possible before. But here's what really gets me, the part that makes this more than just a scientific curiosity. When you look at Bernardinelli Bernstein, when you see those carbon monoxide emissions streaming off its surface, you're not just looking at a comet, you're looking at the breath of the early solar system. You're watching molecules that have been frozen for more than 4 billion years begin to move again, to warm, to escape into space and scatter into the void. Those molecules were there when the Earth was forming. They were there when the first oceans condensed on our planet's surface. They were there when life began, and they've been waiting, unchanged, in the cold and the dark ever since. Now for this brief window of time, they're visible. They're measurable. They're telling us a story about where we came from and what the raw materials of our cosmic neighbourhood really look like when they haven't been cooked, crushed, or chemically altered by billions of years of planetary geology. And it's not just about the past. Understanding the composition and behaviour of objects like Bernardinelli Bernstein has real implications for how we think about the delivery of volatiles to planets, including Earth. The water in our oceans, the carbon in our atmosphere, the organic molecules that form the basis of life, all of those things had to come from somewhere. Some of it was here from the beginning, baked into the rocks and minerals that coalesce to form the planet. But a significant fraction, maybe even the majority, was delivered later, by impacts from comets and asteroids during the period known as the Late Heavy Bombardment. Those impacts brought water, organics, and other volatiles to the young Earth, transforming it from a dry, barren rock into a world capable of supporting life. Bernardinelli Bernstein is a living example of the kind of object that could have played that role. It's large enough that an impact with a planet, though it would be catastrophic, would also deliver an enormous payload of water and organic material. And if there are many more objects like this out there in the Oort Cloud, as some researchers are starting to suspect, then the process of volatile delivery to planets, both in our solar system and in others, might be more common, more efficient, and more important than we previously thought. So as we watch this time capsule start to breathe, as we measure the gases escaping from its surface and analyze the dust streaming into its coma, we're not just documenting the behavior of one unusual comet. We're gathering data that will help us understand the formation of the solar system, the delivery of life's ingredients to Earth, and the potential for similar processes to occur around other stars, on other worlds, where the same kinds of icy giants might be falling inward from their own distant reservoirs and seeding their own planets with water and organics. That's the scope of what Bernardinelli Bernstein represents. It's not just big, it's not just strange, it's fundamentally important, a key piece of the puzzle that connects the cold, distant edges of our solar system to the warm, living world we inhabit. And now, with that perspective in mind, let's turn to the comparison that makes this object's strangeness even more striking. Because for all the attention that small interstellar visitors have received, it's this silent giant that truly challenges our assumptions. You've probably heard the excitement in recent years whenever a new interstellar visitor is detected passing through our solar system. These are objects that don't belong to us, that formed around other stars and have been wandering through the galaxy for who knows how long before their paths happen to intersect with ours. They're exotic, mysterious, and fleeting, here for a brief moment and then gone forever, back into the depths of interstellar space with no intention of returning. Objects like 3I Atlas capture the imagination because they represent the rare chance to study material from beyond our solar system without having to send a probe across light years of empty space. They're cosmic messengers, bringing news from distant star systems in the form of their composition, structure, and behavior. And every time one is discovered, it's a headline event, with researchers scrambling to gather as much data as possible before the object fades from view. But let's be honest about what these objects actually are. They're small. Interstellar comets like 3I Atlas have nuclei that measure at most a few kilometers across, often much less. They're fragments, pieces of debris that were probably ejected from their home systems during the chaotic process of planet formation. When gravitational interactions between forming planets and smaller bodies sent countless objects flying into interstellar space, they're moving fast, not just by our standards but by solar system standards, because they're not gravitationally bound to our sun. They pass through on hyperbolic trajectories, picking up speed as they fall toward the sun, and then whipping back out again, accelerated by the very gravity well they briefly entered. They don't linger, they don't slow down, they don't give us time to send a mission, or even to gather more than a few weeks or months of observations, before they're too far and too faint to study anymore. And while that makes them exciting, it also makes them limited in what they can tell us. We get a glimpse, a snapshot, and then they're gone. Now let's talk about Bernardinelli Bernstein. This thing is not small. Its nucleus, as we've established, is somewhere in the range of 120 to 140 kilometers across, depending on how reflective its surface is and how much material has been shed or buried over time. That makes it tens of thousands of times more massive than a typical interstellar comet. Not a few times larger, tens of thousands. The difference in mass is so extreme that comparing them is almost meaningless, like comparing a pebble to a house. Bernardinelli Bernstein isn't just a comet, it's a dwarf planet-scale object, something that has enough mass and size to be gravitationally rounded, to have internal structure, to potentially have differentiated layers of ice and rock that formed early in its history when it was still warm from the energy of its own formation. And yet, despite that size, it's behaving like a comet, outgassing, forming a coma, shedding material as it approaches the sun. That combination, That blending of comet-like activity with dwarf planet-like size is what makes it so strange and so difficult to categorize. And here's the other key difference. Bernardinelli Bernstein is ours. It's not passing through. It's not an interstellar visitor on a one-time trajectory. It's bound to the Sun, gravitationally tethered by an orbit that, while extreme, is still an ellipse. It will come in, it will reach perihelion, and it will go back out. But it will return. It belongs to the solar system the same way Earth and Jupiter and Neptune do. It's part of the family. But it's a member of the family that spends almost all of its time in the distant reaches, in the Oort Cloud, where the Sun's influence is so weak that it's almost negligible, where the cold is so profound and the isolation so complete that these objects might as well be interstellar. For all practical purposes, Bernardinelli Bernstein has spent the vast majority of its existence in a realm that's closer to deep space than to the planetary system, and now it's coming back, descending into the light, becoming visible and measurable for the first time in hundreds of thousands of years. So when I say that Bernardinelli Bernstein is stranger than 3i Atlas, I'm not saying it's more dangerous or more exotic in the sense of being from another star. I'm saying it's more challenging to our understanding of what should and shouldn't exist in our solar system. Interstellar visitors are expected. We know that planet formation is a messy process, and we know that many star systems eject small bodies into interstellar space. So finding a few of them passing through ours is not surprising. It's actually reassuring, because it confirms that the models are right and that the galaxy is full of these small wandering fragments. But finding something like Bernardinelli Bernstein, a massive pristine comet on an orbit that takes it from the edge of the Oort Cloud all the way into the outer planets, is not something the models easily predicted. Objects this large are supposed to be rare. The processes that scattered smaller bodies out to the Oort Cloud should have been less efficient at flinging larger ones, because larger objects have more inertia and require more energy to move. So either the scattering process was more violent and energetic than we thought, or there's something about the early dynamics of the solar system that we're still missing, some population of large bodies that got ejected and are still out there, quietly orbiting in the dark. That brings us to a subtle but important point. Bernardinelli Bernstein challenges the mass distribution models of the Oort Cloud. Before this object was discovered, estimates of how many large bodies, meaning things with diameters of tens or hundreds of kilometers, should be in the Oort Cloud were based on extrapolations from the distribution of smaller comets and asteroids, combined with models of how planet formation and scattering work. Those estimates suggested that large bodies should be quite rare, with most of the Oort Cloud's population consisting of smaller objects in the range of a few kilometers or less. But now we have a clear example of something much larger, something that sits at the high end of the size distribution, and it raises the question, if we found one, how many more are out there? Is Bernardinelli Bernstein an outlier, a statistical fluke, the only giant in a sea of small objects? Or is it the first clear look at a whole class of large distant bodies that we simply haven't been able to detect until now because they're so faint and so far away? Some researchers, in preliminary discussions and early papers, have started to float the idea that the population of large Oort Cloud objects might be higher than current models predict. If that's true, it would have significant implications, not just for understanding the history of our own solar system, but for thinking about how common such populations might be around other stars, and what role they might play in delivering volatiles and organics to planets over billions of years. It's still an open question, still a subject of active research and debate. But the existence of Bernardinelli Bernstein is a data point that can't be ignored. It's proof that these giants exist, that they can survive for billions of years in the outer reservoir, and that they occasionally make their way back into the inner system where we can see them. And here's the psychological shift I want you to make, because it's easy to get lost in the numbers and the comparisons and miss the larger picture. When we talk about interstellar visitors, we're talking about strangers, about objects that belong to someone else's cosmic neighborhood and are just passing through ours. They're interesting, yes, but they're not ours, and they don't tell us much about the structure and history of our own solar system. Bernardinelli Bernstein is different. This is our object. This is a piece of our history, a relic from the formation of the planets, a survivor that got flung outward and has been waiting ever since, preserved in the cold, carrying information about what the early solar system looked like and how it evolved. And now, for this brief moment, it's coming back into the light, giving us a chance to study it in detail, to measure its composition and structure, to understand what it's made of and how it behaves. That's not just scientifically valuable, it's existentially significant. It's a reminder that the solar system we think we know, the one with 8 planets and a handful of dwarf planets and some comets and asteroids, is only the visible part of a much larger, much stranger structure, and the real mysteries, the real giants, are out there in the dark, moving slowly, patiently, on orbits that will eventually bring them back into our view if we're watching carefully enough. So now, with that sense of scale and strangeness firmly in mind, let's zoom out even further and look at the hidden ocean of giants from which Bernardinelli Bernstein emerged. Imagine standing on a beach at night, looking out over a dark ocean that stretches to the horizon and beyond, so vast and so black that you can't see where it ends. Now and then, a wave crests and catches the moonlight, glowing briefly before it fades back into the darkness. You see one wave, then another, separated by long stretches of time and distance, and you begin to wonder, how many waves are out there that I'm not seeing? How deep is this ocean? What lies beneath the surface, moving in currents I can't detect, rising and falling in rhythms I can't predict? That's the Oort Cloud. It's not a physical structure you can touch or photograph. It's a region, a concept, a spherical shell of icy debris that surrounds our solar system at distances so immense that even the fastest spacecraft we've ever built would take tens of thousands of years to reach it. And we can't see it directly. Not as a whole, anyway. We only know it exists because of the comets that occasionally fall inward from that realm, like those rare, glowing waves, giving us brief glimpses of what's out there in the dark. The Oort Cloud is thought to extend from somewhere around a few thousand astronomical units out to as much as 100,000 astronomical units or more, forming a roughly spherical halo around the Sun and the planetary system. To put that in perspective, Neptune, the outermost major planet, orbits at about 30 astronomical units. The Kuiper Belt, the region beyond Neptune where Pluto and other dwarf planets reside, extends out to maybe 50 or 60 astronomical units. The scattered disk, where the most distant known objects with extreme orbits wander, might reach a few hundred astronomical units. But the Oort Cloud, it starts where all of those regions end and extends outward into a volume of space so large that the Sun's gravity is barely stronger than the combined pull of the Milky Way's gravitational field and the tugs from passing stars. This is the true edge of the solar system, the boundary where ours and interstellar space blur into each other, where objects are so loosely bound that a gentle nudge from a distant star or a slight shift in the galactic tide can send them falling inward or fling them out into the galaxy forever. We think the Oort Cloud was populated during the chaotic early days of the solar system, when the giant planets were still migrating and their gravitational interactions were scattering smaller bodies in all directions. Objects that formed in the region where the giant planets now orbit, where there was abundant water ice, carbon dioxide, methane, and other volatiles, were either accreted into the planets and moons or flung outward by close gravitational encounters. Some of those ejected objects had just the right velocity and trajectory to settle into distant, stable orbits, far from the Sun but still gravitationally bound. Over millions of years, billions of such objects accumulated in the Oort Cloud, forming a reservoir of primordial material that has remained largely unchanged since the solar system's youth. And because those objects are so far away, they're preserved in a deep freeze, their surfaces and interiors barely altered by the weak sunlight and rare collisions that occur at such extreme distances. They're time capsules, frozen samples of the material that went into making the planets, waiting in the dark until something nudges them inward and they begin their long fall toward the Sun. But here's the unsettling question. How many of them are there, and how large can they get? Standard models estimate that the Oort Cloud contains trillions of objects, maybe more, with a total mass somewhere in the range of a few Earth masses, possibly up to several times that, depending on the assumptions you make about the size distribution and the efficiency of the scattering process. Most of those objects are thought to be small, comets with nuclei just a few kilometers across, maybe 10 or 20 at most, the kinds of objects we see when they come close to the Sun and light up with bright comas and tails. But the models also allow for a smaller number of larger objects, things in the size range of tens or hundreds of kilometers, dwarf planet-scale bodies that got scattered outward during the same chaotic period, but were rare enough that we haven't seen many of them yet. Bernardinelli Bernstein is almost certainly one of those rare larger objects, and the fact that we found it, that we detected it while it was still far enough out that it was barely visible, suggests that there might be more of them out there than we thought. Some researchers, looking at the implications of Bernardinelli Bernstein's size and orbit, have started to suggest in preliminary discussions and preprints that the Oort Cloud's population of large bodies might be higher than current estimates predict. If the scattering process that populated the Oort Cloud was efficient enough to send something as massive as Bernardinelli Bernstein out to those distances, then it's reasonable to ask whether other large objects were also ejected and are still out there. Too faint and too distant for us to see with current surveys. This is not a wild guess. It's a logical inference based on the statistics of one data point. If Bernardinelli Bernstein is one of, say, 100 or 1,000 such large objects in the Oort Cloud, then we should expect to see more of them as our surveys improve and as we get better at detecting faint, distant objects moving slowly across the sky. And if there are more of them, if the Oort Cloud contains a population of giant comets that we've only just begun to discover, then our understanding of the solar system's architecture, its mass distribution, and the processes that shaped it will need to be revised. But let's be clear about what we know and what we're guessing. We know that Bernardinelli Bernstein exists. We know its size, its orbit, its composition. We know it came from the Oort Cloud, and we know that similar objects must exist, because the processes that created it are not unique. They're part of the standard picture of planet formation and dynamical evolution. What we don't know is how many more there are, how large the largest ones can be, and whether there are other populations of large, distant bodies that we haven't detected yet because they're even farther out, or on orbits that don't bring them close enough to the Sun for us to see them. That's the frontier we're exploring now, the edge of our knowledge, and Bernardinelli Bernstein is the first clear signpost telling us that the frontier is not as empty as we thought. Think of the Oort Cloud as a dark ocean, and think of the comets we see as the rare waves that rise high enough to catch the light. Bernardinelli Bernstein is one of those waves. A big one, a rare one, but still just one. And if we're seeing one wave of that size, it's reasonable to ask, what else is out there in the depths, moving in currents we can't see, rising and falling in patterns we don't yet understand? Are there other giants, even larger, on orbits that will bring them inward decades or centuries from now? Are there populations of smaller but still significant bodies that could be nudged into the inner solar system by the same forces that sent Bernardinelli Bernstein on its path? And if so, what does that mean for our long-term safety, for our ability to predict and prepare for potential impacts, and for our understanding of how common such reservoirs of icy debris are around other stars? These are not idle questions. The Oort Cloud is not just a curiosity or a distant abstraction. It's a real, physical part of our solar system, a region that contains a significant fraction of the system's total mass in the form of small, icy bodies, and potentially a much larger fraction if there are more giants like Bernardinelli Bernstein than we currently realize. And because the Oort Cloud is so loosely bound, because its inhabitants are so easily perturbed by external forces, it represents a kind of dynamic reservoir, a source of objects that can be nudged inward at any time, on timescales ranging from thousands to millions of years, depending on the strength and timing of the perturbations. We are living in a period when at least one such object has been nudged inward, and is now visible to us. But there's no reason to think that this is the only time it's happened, or that it won't happen again in the future. In fact, given the statistics and the models, it's almost certain that there are other objects on similar paths, objects that have already been nudged and are now falling inward, but are still too far away for us to detect with current technology. And when those objects do become visible, when the next Bernardinelli Bernstein or something even larger emerges from the dark, we'll have another chance to refine our models, to test our predictions, and to understand the true shape and population of the hidden ocean that surrounds us. So as we watch this giant move through the light, as we measure its properties and track its evolution, we're not just studying one object. We're learning how to see the ocean itself, how to read the patterns and predict the waves, how to understand the forces that shape the orbits of things so distant and so cold that they exist in a twilight zone between planetary science and interstellar astronomy. And that brings us to the next question, the one that's been lurking beneath everything we've talked about so far. What actually nudged this giant? What force or encounter or resonance set it on the path that brought it here, now, visible to us for the first time in hundreds of thousands of years? That's where we turn next, into the mechanics of nudging giants and the unsettling possibility that the forces at work are more subtle and more mysterious than we've been willing to admit. This is the question that keeps circling back, the one that doesn't have a clean, simple answer, no matter how much we want one. What set Bernardinelli Bernstein on the path that brought it here? Comets don't just decide to fall inward on their own. They're not conscious, they don't have agency. They're chunks of ice and rock, moving according to the laws of gravity, following trajectories that are determined by the forces acting on them. So if Bernardinelli Bernstein is now descending toward the inner solar system on a path it hasn't followed in hundreds of thousands of years, something must have changed. Something must have nudged it, altered its orbit, given it just enough of a gravitational kick to start the long, slow fall. And the uncomfortable truth is that we don't fully know what that something was. We have candidates, we have models, we have ideas that range from well-established astrophysical processes to speculative hypotheses that are still being debated. But we don't have a single definitive answer, a smoking gun that says, this is what did it. Let's start with the most straightforward mechanisms, the ones that are well understood and widely accepted. The first is the galactic tide. Our solar system is not floating in empty space. It's orbiting the centre of the Milky Way galaxy, along with hundreds of billions of other stars, in a slow, stately dance that takes us around the galactic centre once every couple of 100 million years. As we move through that orbit, we're not just being pulled by the sun's gravity, we're also being pulled by the combined gravity of all the other stars and dark matter in the galaxy, a diffuse but ever-present force that acts on everything in the solar system, including the distant objects in the Oort Cloud. Because the Oort Cloud is so far from the sun's gravity there is weak, and the galactic tide becomes significant. Over millions of years, that tide can slowly change the orbits of Oort Cloud objects, increasing or decreasing their orbital energy, tilting their orbital planes, and occasionally nudging them onto paths that bring them closer to the sun. It's a slow process, a gradual reshaping of orbits that happens over timescales far longer than human civilization, but it's always at work, and it's one of the main mechanisms by which Oort Cloud comets are sent inward. The second mechanism is stellar flybys. The sun is not alone in its journey through the galaxy. Every few million years, on average, another star passes close enough to the outer edge of the Oort Cloud that its gravity can significantly perturb the orbits of objects there. These encounters are usually distant. Most stars that pass by come no closer than a light year or so, which is still tens of thousands of astronomical units. But even at that distance, the gravitational influence of a passing star can be enough to change the velocities and trajectories of Oort Cloud objects by small but meaningful amounts. If a star passes through or near the Oort Cloud, it can scatter objects inward, outward, or even eject them from the solar system entirely. We have catalogues of nearby stars whose past trajectories brought them within range of our system, and we can calculate, at least in principle, which of those encounters might have perturbed which comets. But matching a specific comet to a specific stellar encounter is difficult, because the Oort Cloud is so vast and the perturbations are so subtle. Still, this is a known, well-understood process, and it's likely responsible for sending many long-period comets on their inward journeys. So far, so good. Galactic tide, stellar flybys, these are the standard explanations, the ones you'll find in any textbook on solar system dynamics. But here's where it gets less certain. When you try to back-integrate the orbit of Bernardinelli Bernstein, when you run the numbers and ask what combination of forces would produce an orbit with its specific eccentricity, inclination and timing, the picture becomes murkier. The general features, long period, high eccentricity, large inclination, can be explained by galactic tide and stellar encounters, but the precise combination of those features, especially the extreme tilt and the fact that it's coming in now, at this particular moment in the solar system's history, is harder to pin down to a single cause. It could be a combination of multiple perturbations over time, each one tweaking the orbit slightly until it reached its current configuration. It could be one particularly close stellar flyby that happened 1 million or so years ago and gave the object a strong enough kick to start it falling. Or it could be something else, something more subtle, that we haven't fully accounted for in the models. This is where the conversation starts to edge into more speculative territory, and I want to be very clear about what is established and what is still hypothetical. One idea that has been circulating in the research community, particularly in the context of explaining the strange orbits of some trans-Neptunian objects, is the existence of a distant, undiscovered planet, commonly referred to as Planet 9. If such a planet exists, it would be a world several times the mass of Earth, orbiting far beyond Neptune, taking thousands of years to complete a single orbit. Its gravity would be weak at any given location, but over long timescales, millions of years, it could shape the orbits of distant objects in subtle but detectable ways. Some researchers have pointed to clustering patterns in the orbits of certain trans-Neptunian objects as evidence for this hypothetical planet, arguing that the observed alignments are too unlikely to be the result of chance alone. But as of now, Planet 9 has not been directly detected. We don't have an image of it, we don't have a confirmed position, and while the circumstantial evidence is intriguing, it's not conclusive. So when we ask whether something like Planet 9 could have played a role in nudging Bernardinelli Bernstein onto its current path, the answer is maybe, it's possible, but it's not proven, and invoking it as an explanation is, at this stage, more of a suggestion than a definitive answer. There are even more speculative ideas floating around in the physics and astronomy discussion circles, things that show up in preprints and conference talks, but haven't yet been fully tested or accepted by the broader community. Some researchers have explored the idea that dark matter, the mysterious invisible substance that makes up most of the matter in the universe, might not be perfectly uniform in its distribution. If there are small-scale inhomogeneities in the dark matter density, regions where it's slightly clumped or slightly rarefied, then the gravitational effects of those variations could, over millions of years, subtly influence the orbits of distant solar system objects. This is a fringe idea, one that's hard to test with current observations, but it's not completely without basis. We know dark matter exists, we know it exerts gravity, and we know there are still many unknowns about its distribution and behaviour on small scales. Similarly, there's been some theoretical work on whether long-term resonances with the galactic tide, or interactions with structures in the galaxy that we don't fully map yet, could create periodic perturbations that affect Oort Cloud objects in ways we haven't accounted for. Again, these are hypotheses, not established facts, and they should be treated as such. The point I'm making is this. We can run the orbit of Bernardinelli Bernstein backwards under known gravitational forces, and we can produce scenarios that roughly match its current trajectory. But we can't point to a single event or a single object and say with certainty, that is what nudged it. The most likely explanation is some combination of galactic tide and stellar encounters, possibly with contributions from other, less well-understood factors. But the lack of a clear, definitive answer is itself significant. It tells us that the dynamics of the outer solar system are more complex, more sensitive to small perturbations, and less deterministic than we'd like to think. It tells us that our models are good, but not perfect, and that there's still a lot we don't know about the forces that shape the orbits of these distant giants. And here's the unsettling part. If we don't fully understand what nudged Bernardinelli Bernstein, then we can't fully predict when the next giant will be shaken loose and start its own fall toward the Sun. We can make statistical predictions. We can say that, on average, a certain number of large comets should be perturbed and sent inward every million years or so, but we can't predict specific objects or specific times. The Oort Cloud is a dynamic reservoir, constantly being stirred by forces we can measure and forces we can only guess at, and Bernardinelli Bernstein is proof that sometimes one of those stirrings results in something massive and strange emerging from the dark. So as we continue to track this object, as we watch it approach perihelion and measure its properties in ever greater detail, we're also learning how to read the signs, how to look for other objects that might be on similar paths, and how to improve our models so that the next time a silent giant slides into view, we're not surprised, we're ready. But before we get ahead of ourselves, let's focus on what's happening now, in real time, as this ancient block of ice wakes up and gives us the chance to study it like never before. There's something almost hypnotic about watching a comet come to life. It's a slow process, nothing like the sudden drama of an impact or the explosive violence of a supernova. It unfolds over months and years, a gradual brightening, a spreading cloud of gas and dust that grows larger and more diffuse as the comet continues its inward journey. You watch it night after night, tracking its position against the background stars, measuring the intensity and distribution of the light it reflects, and you begin to see patterns, small jets of gas erupting from specific areas of the nucleus, asymmetries in the coma that hint at rotation and surface features, subtle changes in colour and brightness that tell you which ices are sublimating and at what rates. It's detective work, puzzle solving on a cosmic scale, and every new observation adds another piece to the picture. With Bernardinelli Bernstein, that process is just beginning. And because this comet is so large, so distant, and so well positioned for long-term monitoring, we have an opportunity that rarely comes along. The chance to watch a truly giant comet wake up over the course of years, in real time, with the full arsenal of modern astronomy at our disposal. Right now, as I'm speaking to you, Bernardinelli Bernstein is still far from its perihelion, still beyond the orbit of Uranus, but close enough that ground-based telescopes and space observatories can track it and gather data. The Hubble Space Telescope has already imaged it multiple times, resolving the coma and even getting hints of the nucleus itself, trying to separate the faint reflected sunlight from the solid core from the much brighter glow of the surrounding gas and dust. The Atacama Large Millimeter Array, one of the most powerful radio telescope facilities on Earth, has detected carbon monoxide emissions streaming from the comet, giving us direct spectroscopic evidence of what's sublimating from the surface. Other observatories, both professional and amateur, are tracking its brightness and position, building up a database of observations that will allow researchers to model the comet's activity in unprecedented detail. And as the comet continues to approach the Sun, as the sunlight grows gradually stronger and the surface temperature rises, that activity will only increase. By the time Bernardinelli Bernstein reaches perihelion in January of 2031, it should be fully active. The coma, the cloud of gas and dust surrounding the nucleus, will likely be large and bright enough that even amateur astronomers with good telescopes will be able to see it as a fuzzy, diffuse patch of light moving slowly against the stars. It won't be a spectacular naked-eye object. Perihelion is still beyond Saturn's orbit, still far from the Sun, so the comet will never get the kind of intense heating that produces the brilliant, long-tailed comets we see in historical records and dramatic photos. But it will be visible, measurable, and scientifically rich. And because it's so large, because it has so much material to shed, that activity will likely continue for an extended period, giving researchers months or even years of high-quality data to work with. What will scientists be looking for? Everything. The first priority is composition. By analysing the gases streaming off the comet using spectroscopy, researchers can identify which molecules are present and in what abundances. Water, carbon monoxide, carbon dioxide, methane, ammonia, hydrogen cyanide, formaldehyde, all of these have distinctive spectral signatures, and measuring their ratios will tell us about the conditions in the protoplanetary disk when Bernardinelli Bernstein formed, and how those conditions varied with distance from the Sun. Isotope ratios, particularly the ratio of deuterium to hydrogen in water molecules, are especially important because they act as fingerprints, telling us whether the water in comets like this is similar to the water on Earth, or whether it's distinct, which has implications for understanding how Earth got its oceans. Then there's the dust. By studying the size distribution, composition, and reflectivity of the dust particles in the coma, scientists can learn about the structure and chemistry of the nucleus's surface and interior, and how those have been altered, or not altered, over billions of years. And then there's the activity itself, the patterns and dynamics of how the comet sheds material. Comets don't sublimate uniformly. They have active regions, areas where jets of gas burst from the surface, driven by the pressure of sublimating ice beneath a layer of insulating dust. By tracking where those jets are and how they change over time, researchers can infer the nucleus's rotation state, its surface topography, and the distribution of different ice types. With Bernardinelli Bernstein, because the nucleus is so large, there's the possibility of detecting very complex surface features, maybe even seasonal variations as different regions rotate into and out of sunlight. And all of that data will feed back into models of how comets form, how they evolve, and what role they play in the broader dynamics of the solar system. But let's talk about something that's probably on your mind, because it's the question I get asked most often when I talk about large objects approaching from the outer system. Is Bernardinelli Bernstein dangerous? Is it going to hit Earth? And the answer, fortunately, is a very clear no. Its orbit has been calculated with high precision, and perihelion, the closest it will ever get to the Sun, will place it around 10 to 11 astronomical units from the Sun, which is just beyond Saturn's orbit. Earth, by contrast, orbits at 1 astronomical unit. That means that at closest approach, Bernardinelli Bernstein will still be 10 times farther from the Sun than we are, and the geometry of the orbits is such that there is no chance of a collision, or even a close approach. The orbital planes are tilted relative to each other, and the timing is all wrong. When the comet reaches perihelion, Earth will be on the opposite side of the Sun, nowhere near the comet's path. So while Bernardinelli Bernstein is massive, strange, and scientifically fascinating, it poses no impact threat to our planet. It's not coming for us. It's just passing through the outer neighbourhood, close enough for us to study but far enough away to be completely safe. And that's actually the ideal scenario. We get to watch this object, to measure it, to learn from it, without any of the anxiety or risk that would come from an actual close approach. It's a cosmic laboratory, a moving, evolving sample of primordial ice that we can observe with every tool we have, and there's no rush, no countdown, no single fleeting moment when we have to get all our observations done before it disappears. The approach to perihelion will unfold over years, and the retreat back out into the darkness will take just as long, giving us a long baseline of data that will be invaluable for understanding not just this comet, but comets in general, and the processes that govern their behaviour. And here's the part that really gets me, the reason I think Bernardinelli Bernstein matters beyond the science. This is a once-in-civilization event. No one alive today will see it return. The last time this object passed through the inner solar system, humans didn't exist. The next time it passes through, hundreds of thousands of years from now, whatever intelligent life exists at that point will have no connection to us, no memory of us, no way to know that we were here, watching, measuring, trying to understand. This is our moment. This is the window when Bernardinelli Bernstein is visible, when it's close enough to study, when we can gather data that will inform not just our understanding of this one object, but our broader picture of the solar system's architecture, its history, and the processes that have shaped it over billions of years, and that data will outlast us. It will be part of the scientific record for as long as human civilization, or its descendants, continue to exist. So in a very real sense, by watching this giant wake up, by tracking its journey and analysing its composition, we're not just doing science, we're bearing witness to a cosmic event that connects us to the deep past and the distant future in a way that very few phenomena can. So as the years progress, and Bernardinelli Bernstein continues its slow fall toward perihelion, keep an eye on the news, on the updates from observatories, on the papers that will be published as new data comes in. Because each new observation, each new spectrum, each new measurement of brightness or gas production or dust distribution is a piece of a much larger story. The story of what Bernardinelli Bernstein is, where it came from, and what it tells us about the hidden ocean of giants from which it emerged. And that story in turn is part of an even larger narrative, one that asks not just about this object or this solar system, but about the nature of planetary systems in general, the delivery of water and organics to planets, and the role that these silent giants play in shaping the conditions for life. That's where we turn next. When you think about the history of the Earth, about how our planet came to be a living, breathing world, with oceans and an atmosphere and the conditions necessary for life, it's easy to focus on the big events, the formation of the planet from the protoplanetary disk, the giant impact that created the moon, the cooling of the surface, the first appearance of liquid water. But there's another part of the story, a quieter but equally important chapter that involves delivery, not formation, but delivery. Because the Earth, when it first coalesced from the dust and rock of the inner solar system, was probably relatively dry. The region where Earth formed, close to the Sun, was too hot for water ice to survive. Water ice, along with other volatile compounds like carbon dioxide, methane and ammonia, could only condense farther out, beyond what's called the snow line or frost line, the distance from the Sun where temperatures drop low enough for these substances to freeze. So if Earth started out mostly dry, where did the oceans come from? Where did the water and the organics and the other volatiles that make up our atmosphere and biosphere come from? The answer, at least in part, is that they were delivered later, during a period of heavy bombardment when comets and asteroids from the outer solar system rained down on the inner planets, bringing with them the ingredients for oceans and life. Bernardinelli Bernstein is a living example of the kind of object that could have played that role. It's a massive block of ice, rich in water and carbon compounds, formed in the cold outer regions of the early solar system and preserved in a deep freeze for billions of years. If an object like this were to collide with a planet, and I want to be very clear that Bernardinelli Bernstein itself is not on a collision course with Earth, it would deliver an enormous payload of volatiles. We're talking about a nucleus over 100 kilometers across, with a mass that could be measured in trillions of tons. An impact from something that size would be catastrophic, yes, but it would also fundamentally change the composition and chemistry of the planet it hit. It would add water, organics, and other volatiles to the surface and atmosphere, potentially creating or replenishing oceans, thickening the atmosphere, and seeding the planet with the raw materials needed for life. And if there are many more objects like Bernardinelli Bernstein in the Oort Cloud, as some researchers are starting to suspect, then the process of volatile delivery to planets, both in our solar system and in others, might be more common, more efficient, and more important than we previously thought. Think about the implications of that. The current models of how Earth got its water involve a combination of sources. Some water was probably trapped in the minerals of the rocky material that formed the planet, released over time through volcanic outgassing. Some was delivered by asteroids from the asteroid belt, which can contain significant amounts of water bound up in their minerals, and some, perhaps a significant fraction, was delivered by comets from the outer solar system. But the relative contributions of those sources are still debated. Some isotopic measurements suggest that cometary water is slightly different from Earth's water, specifically that it has a higher ratio of deuterium to hydrogen, which would imply that comets were not the dominant source. But other measurements, from different comets and different types of water-bearing objects, show ratios that are closer to Earth's, suggesting that the picture is more complicated and that there might be multiple populations of comets with different isotopic signatures. Bernardinelli Bernstein, as a pristine Oort Cloud object, will add crucial data to that debate. By measuring the isotopic composition of the water and other volatiles streaming off this comet, scientists can compare it to the ratios found on Earth, in other comets, and in asteroids, helping to narrow down which sources contributed what fractions to Earth's oceans. And it's not just about Earth. The same processes that delivered water and organics to our planet likely operated, and may still be operating, on other worlds in the solar system. Jupiter's moon, Europa, Saturn's moon, Enceladus, Neptune's moon, Triton. All of these are icy worlds with subsurface oceans or active geology driven by the presence of volatiles. Some of those volatiles were probably there from the beginning, incorporated into the moons when they formed. But some might have been delivered later by cometary impacts, and understanding the composition and dynamics of objects like Bernardinelli Bernstein helps us understand how those delivery processes work. Similarly, when we look at exoplanets, at the thousands of worlds orbiting other stars that we've discovered in recent years, we have to ask the same questions. How do those planets get their water? How do they get their atmospheres? Are there reservoirs of comets and icy bodies around other stars, similar to our Oort Cloud, that deliver volatiles to planets over millions or billions of years? And if so, how common is that process, and how important is it for the emergence of habitable conditions? Bernardinelli Bernstein doesn't answer all of those questions, but it gives us a data point, a concrete example of what a large, volatile-rich body from the outer solar system looks like, how it behaves, and what it's made of. And by studying it in detail, we're building a framework that can be applied to other systems, other comets, and other planets. We're learning how to read the signatures of volatile delivery, how to recognize the patterns and processes that shape planetary chemistry, and how to connect the cold, distant reaches of a star system to the warm, living worlds that orbit closer in. There's another angle to this, one that's more speculative but still worth considering. Some researchers have pointed out that if the Oort Cloud contains more large bodies than current models predict, if Bernardinelli Bernstein is not an isolated anomaly but rather the first clear detection of a more populous class of objects, then the total mass of the Oort Cloud might be higher than we thought, and the potential for volatile delivery to planets might be correspondingly greater. Over the billions of years of a planetary system's history, a steady trickle of large comets falling inward and occasionally impacting planets could add up to a significant amount of water and organics, possibly even enough to transform dry, rocky worlds into habitable ones. That's a long-term process, one that happens over timescales far longer than human history, but it's a process that might be fundamental to how planetary systems evolve and how life emerges. And if it's happening here, around our Sun, there's no reason to think it's not happening around other stars as well. So when we watch Bernardinelli Bernstein, when we measure its composition and track its activity and analyze the data we gather, we're not just learning about one comet, we're learning about the mechanisms that connect star formation, planet formation, volatile delivery, and the emergence of conditions suitable for life. That's a grand narrative, one that spans billions of years and ties together processes happening on scales from interstellar clouds down to individual molecules on planetary surfaces. And Bernardinelli Bernstein, this silent giant that spent most of its existence in the cold and the dark, is a key character in that narrative, a messenger from the outer reaches carrying information about the past, present and future of our solar system, and others like it. But of course, no discussion of an object this strange and this large would be complete without addressing the rumours, the misconceptions, and the outright speculation that have sprung up around it. That's where we go next, into the realm of what we don't know, what we think we might know, and what's just noise. Whenever an unusual object enters the public consciousness, especially one with numbers as extreme as Bernardinelli Bernstein's, it's inevitable that rumours and misconceptions will follow. That's not a criticism, it's human nature. We see something strange, something that doesn't fit our everyday experience, and our minds reach for explanations, for narratives, for ways to make sense of it. Sometimes those narratives are grounded in misunderstanding. Sometimes they're fueled by anxiety, and sometimes they're deliberate exaggerations or distortions spread by people who either don't know better or who benefit from generating fear and clicks. So let's take a moment to separate what we actually know about Bernardinelli Bernstein from what's circulating in online spaces, and to be very clear about what is established fact, what is open scientific question, and what is unfounded speculation. First, the most persistent and most easily dispelled rumour, that Bernardinelli Bernstein is on a collision course with Earth, or that it poses any kind of imminent threat to our planet. This is false. The orbit has been calculated with high precision, using observations that span years and that give us a very accurate picture of where the comet has been, where it is now, and where it's going. Perihelion, the closest point in its orbit to the Sun, will place it just beyond Saturn's orbit, at a distance of a little over 10 astronomical units from the Sun. Earth orbits at 1 astronomical unit. At no point in the foreseeable future will Bernardinelli Bernstein come anywhere near Earth. The orbital planes are tilted relative to each other, the timing is wrong, and there is simply no scenario under current gravitational models where a collision or even a close approach is possible. If you've seen headlines or videos claiming otherwise, claiming that this comet is heading for Earth or on a doomsday trajectory, those are either misunderstandings or deliberate misrepresentations designed to generate fear and engagement. The actual science says the opposite. This comet is safe, distant, and will remain so. Second, there have been some online discussions linking Bernardinelli Bernstein to the hypothetical Planet 9, sometimes going so far as to suggest that the comet's orbit is proof of Planet 9's existence, or that Planet 9 is somehow steering the comet toward us. Let's be clear about this. Planet 9, if it exists, is a hypothetical distant planet that some researchers have proposed to explain clustering patterns in the orbits of certain trans-Neptunian objects. It has not been directly detected. We don't have an image of it, we don't have a confirmed position, and while the circumstantial evidence is interesting and worth investigating, it's not conclusive. Could something like Planet 9 have played a role in perturbing Bernardinelli Bernstein's orbit over millions of years? Possibly. It's one of several mechanisms that could contribute to the orbit's current shape, but it's not proven, and it's certainly not the case, that Planet 9 is steering this comet in any deliberate or directed sense. Gravity doesn't work that way. Orbits are the result of many forces acting over long timescales, and while a distant massive planet could be one of those forces, it's not a controlling hand, it's just one more gravitational influence among many. Third, there have been more exotic and speculative ideas circulating, things that link Bernardinelli Bernstein to dark matter, to anomalies in the cosmic microwave background, to hidden structures in the outer solar system, and even to the possibility that the comet is artificial or controlled. I want to address these carefully, because some of them touch on real scientific questions, while others are pure fantasy. Let's start with dark matter. Dark matter is a real, confirmed component of the universe. We know it exists because we can see its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the cosmos. But on the scale of individual solar system objects, dark matter's influence is negligible. The density of dark matter in our local neighbourhood is so low that it has no measurable effect on the orbits of planets, comets, or anything else. Some researchers have explored in theoretical papers the idea that if dark matter is not perfectly uniform, if there are small-scale clumps or filaments, those might exert tiny, long-term gravitational influences on distant objects. But this is highly speculative, untested, and certainly not something we can point to as an explanation for Bernardinelli Bernstein's orbit. It's an interesting idea to explore in models, but it's not an established fact, and claiming that dark matter is steering this comet is not supported by current evidence. As for the idea that Bernardinelli Bernstein is artificial, that it's some kind of spacecraft or probe or controlled object, this is pure science fiction. There is zero evidence for it. The comet behaves exactly as we'd expect a large icy body to behave. It's outgassing volatiles, it has a coma, it's on an elliptical orbit consistent with gravitational dynamics. There are no anomalous accelerations, no signs of propulsion, no signals, no structures. It's a comet. A very large comet, yes, but a comet nonetheless. The reason these ideas persist is that they're dramatic and they feed into a desire for mystery and hidden meaning. But the actual mystery, the real scientific questions about where this object came from, how its orbit evolved, and what it tells us about the Oort Cloud is more than interesting enough without inventing artificial explanations. Now, let's talk about what we genuinely don't know, because there are real uncertainties and open questions, and acknowledging them is important. We don't know, with absolute certainty, what specific event or combination of events set Bernardinelli Bernstein on its current inward path. We have good models that involve galactic tide and stellar flybys, and those models are consistent with the orbit, but we can't point to a single moment and say, this is when it happened. This is the star that passed by. This is the exact perturbation. That level of precision is beyond our current ability to reconstruct, given the timescales involved and the number of variables. Similarly, we don't know how many more objects like Bernardinelli Bernstein are out there in the Oort Cloud. We can make estimates based on models, and on the assumption that this object is representative of a larger population, but those estimates have wide uncertainty ranges. It could be that there are a handful of such large objects, or it could be that there are many hundreds, and we won't know until better surveys detect more of them. We also don't know, in detail, what the interior structure of Bernardinelli Bernstein looks like. Is it a solid, undifferentiated block of ice and rock? Or does it have a layered structure, maybe a rocky core surrounded by an icy mantle, the way some models of large comets and dwarf planets suggest? Does it have internal pockets of volatile rich material that will produce outbursts of activity as they are exposed by sublimation? These are questions that can only be answered through continued observation, and ideally through future missions that could fly by the comet and take close-up measurements. And there are broader questions about the Oort Cloud itself. How is it really populated? What fraction of its mass is in large bodies versus small ones? How stable are the orbits over billions of years? And how often do perturbations send objects inward or fling them out into interstellar space? These are active areas of research, and Bernardinelli Bernstein is helping to refine the answers, but the full picture is still being pieced together. So here's the takeaway. There is real uncertainty, real mystery, and real scientific debate surrounding Bernardinelli Bernstein and what it tells us about the solar system. But that uncertainty is not the same as anything goes. It's not a license to invent wild explanations or to claim that we're being lied to or that there's a cover-up. The scientific process is transparent, the data is available, the models are published, and the uncertainties are acknowledged openly because that's how science works, by identifying what we know, what we don't know, and what we need to find out. As we start to think about what comes after Bernardinelli Bernstein, keep that distinction in mind. The frontier of knowledge is exciting precisely because it's uncertain, because there are still discoveries to be made and questions to be answered, and the way we answer those questions is not by inventing stories, but by watching, measuring, and thinking carefully about what the data is actually telling us. So where does that leave us? we've traced the path of Bernardinelli Bernstein from the distant Oort Cloud to its slow approach toward perihelion in 2031. We've explored why its orbit is so strange, why its size is so unsettling, and why its early activity tells us that this is not just another comet. It's a pristine sample of the early solar system, a time capsule that's only now beginning to open. We've looked at the forces that might have nudged it inward, the uncertainties that still remain, and the ways in which this object challenges our models of the Oort Cloud's population and dynamics. And we've addressed the rumours and misconceptions that swirl around any object this large and this unusual, separating fact from fiction and acknowledging what we genuinely don't know. But the story doesn't end with Bernardinelli Bernstein. This is not a singular, isolated event. This is the beginning of a shift in how we see the outer solar system, a shift from thinking of it as empty and static to recognising it as a dynamic, populated region where giants like this can emerge from the dark at any time. Let me put it plainly. Bernardinelli Bernstein is almost certainly not the only object of its kind. The processes that ejected it to the Oort Cloud billions of years ago, the processes that nudged it onto its current inward path, are not unique. They're part of the standard dynamics of planetary systems, and they've been operating continuously since the solar system formed. That means there are other objects out there, other large, icy bodies orbiting in the distant cold, waiting for their own nudge, their own moment to fall inward and become visible to us. We just haven't detected them yet. And the reason we haven't detected them is not because they don't exist. It's because they're faint, they're far, and until very recently we didn't have the technology or the survey programs capable of finding them. That's changing. Over the next decade, as new telescopes come online and as sky surveys become more sensitive and more comprehensive, we're going to start detecting more of these distant giants. The Vera Rubin Observatory, also known as the Legacy Survey of Space and Time, is expected to begin full operations soon, and it will revolutionize our ability to detect faint, slow-moving objects in the outer solar system. It will scan the entire visible sky repeatedly, building up a database of moving objects that will allow researchers to identify and track comets, asteroids, and trans-Neptunian objects with unprecedented efficiency. And when it does, I can almost guarantee that we'll find more objects like Bernardinelli Bernstein, maybe smaller, maybe even larger, but following similar orbits, carrying similar stories, and raising similar questions about the hidden architecture of the space around us. Each new detection will refine our models. Each new giant will add a data point to the population statistics, helping us understand how many such objects there are, how large they can get, and what role they play in the long-term evolution of the solar system. And over time, those refinements will add up to a fundamentally different picture of the Oort Cloud, not as a static, distant shell of debris, but as a living, dynamic reservoir that's constantly being stirred, reshaped, and occasionally sending its inhabitants inward on journeys that bring them into the light where we can see them. We're living at the moment when that picture is starting to come into focus, when the first clear examples are being detected and studied, and when the tools and techniques to find more are becoming available. That's exciting. That's a privilege. And it means that the story of Bernardinelli Bernstein is not an ending. It's a beginning. Now, let's circle back to the questions I posed at the very start. Because every good investigation has to close its loops. Why did this giant choose now to come in from the deep freeze? The answer, as we've seen, is that now is a somewhat arbitrary label from our perspective. Bernardinelli Bernstein's orbit has been evolving for millions of years under the influence of galactic tides, stellar encounters, and possibly other subtle forces. At some point in that long evolution, it crossed a threshold where its trajectory brought it close enough to the Sun to become detectable. We happened to be here, watching, when that happened. It's not that the comet chose this moment. It's that the dynamics of the outer solar system are such that, every so often, one of these objects completes its long fall and passes through the realm of the planets. We're just lucky enough to be alive and technologically capable of seeing it when it happens. What nudged it out of its distant orbit? We have candidate mechanisms, galactic tides, stellar flybys, possibly contributions from unseen distant planets, or other subtle gravitational influences, but no single definitive answer. The most likely explanation is a combination of factors, acting over millions of years, gradually reshaping the orbit until it took the form we see today. That uncertainty is not a failure of science. It's a reflection of the complexity of the system and the difficulty of reconstructing events that happened over timescales far longer than human civilization. And what else is coming? Almost certainly more giants. We don't know when, we don't know from which direction, and we don't know how large they'll be. But the dynamics that produce Bernardinelli Bernstein are still operating, and the Oort Cloud is still being stirred. Over the coming decades and centuries, more objects will be nudged inward, and some of them will be large, strange, and scientifically rich, just like this one. And when they arrive, we'll be ready. We'll have better telescopes, better models, better understanding of what to look for and what it means. And each new detection will be another piece of the puzzle, another window into the deep structure and history of the solar system. So as Bernardinelli Bernstein continues its slow descent toward the light, as it wakes up more fully and becomes a target for every major observatory on and off Earth, remember what you're witnessing. This is not just a comet. This is a once-in-civilization event, a visitor from the deep past that's giving us a chance to study the raw materials of our solar system in a way that's rarely possible. The data we gather over the next decade will inform our understanding of comets, planet formation, volatile delivery, and the dynamics of the outer solar system for generations to come. And when this giant completes its pass and begins its long retreat back into the darkness, when it fades from view and won't return for hundreds of thousands of years, we'll have captured a moment in time, a snapshot of a slow, patient process that's been unfolding since the planets first formed. And here's my final thought, the one I want you to carry with you. The solar system we think we know, the one with the sun at the centre, and the 8 planets in their neat orbits, and a few comets and asteroids scattered in between, is only the lit, warm, familiar part of a much larger structure. The real solar system extends outward for tens of thousands of astronomical units, into regions so cold and so dark that we can only infer their existence from the rare objects that fall inward and become visible. Bernardinelli Bernstein is a messenger from that hidden realm, a reminder that we're living in a tiny, bright pocket of space that's surrounded by a vast, ancient and largely unexplored darkness. And every so often, something from that darkness slides into the light, and we get a chance to see it, measure it, and learn from it. That's the privilege of being alive in this moment, of having the tools and the curiosity to watch the sky and notice when something strange and beautiful appears. So keep watching, keep asking questions. And when the next silent visitor emerges from the dark, remember, it's not coming for us. It's not a threat. And it's not a mystery in the sense of being incomprehensible. It's a natural, predictable outcome of the forces that shape our cosmic neighborhood, a process that's been happening since the beginning and will continue long after we're gone. But for this brief, shining moment, it's ours to study, ours to understand, and ours to marvel at. If you've stayed with me this far, if you've followed this giant story from the outer darkness to its slow approach into the light, thank you. Hit the like button if this journey resonated with you, and subscribe so you can follow Bernardinelli Bernstein all the way to its 2031 perihelion and beyond. And drop a comment. Tell me where you're watching from, what time it is in your part of the world, because when we talk about objects that spend lifetimes in the cold and only briefly pass through the warmth, it helps to know that we're not alone in paying attention, that there's a community of curious minds out there, scattered across the planet, all looking up at the same sky and asking the same questions. See you in the next one.